In this video, we're going to work some more problems in preparation for the Semester 1 final review for AP Calculus. So here we see in the white the graph of f prime. First, what we're going to do is try to graph its derivative, f double prime. So we can see where there's a horizontal tangent in the f prime function, our f double prime is going to have an x-intercept. We can also see where the f prime function has an inflection point. That's going to be where our negative slopes of tangent lines is going to be its steepest. So that's going to be like a relative minimum. And similarly, once we switch to the positives, where we have an inflection point in f prime, our f double prime is going to have a relative maximum. And there'll be a relative minimum here, and somewhere over here a relative maximum, and somewhere over here a relative minimum. So now as we work our way from left to right, we can see the slopes of the tangent lines here are very close to zero, but a little bit negative. So it's going to have the x-axis as an asymptote. It's going to come down to a relative minimum where we have this inflection point. Then it's going to make its way to zero. And then we're going to work our way up to our relative maximum and back to zero, down to a relative minimum, back to zero, up to a relative maximum, and I didn't quite get that in the right place, but I'll fix that, and back down to our x-axis, and down to a relative minimum. Now as we work our way here, it's getting close to horizontal, which would be a zero derivative, but it's a little bit decreasing, so still a little bit negative. So it's going to approach the x-axis as an asymptote. So there's our f double prime graph. Now you have to change our thinking here, because now we have f prime, and we're going to try to graph y equals f of x. I'm going to slide it up just a little bit here. So now, where this changes sign, we're going from negative to positive, we're going to have a relative minimum. We don't know the y values. Here, we're going to have, it goes from positive to negative, is going to be a relative maximum, and we're going to get our relative minimum here. Now, we'll come back, and where we see these horizontal tangents, this is where our derivative graph is going to be its largest negative. So it's negative, it's getting steeper, steeper, steeper. This is going to be the steepest place, then it's going to continue decreasing, but not as steeply. So this is going to be an inflection point in our original function graph. So each of these relative mins and maxes is going to manifest itself as an inflection point in our graph of f of x. So at the end here, we see that this is a little bit negative, but really close to zero. So our function is, and it doesn't matter where we start this thing, our function is going to be decreasing slowly at first until we get its steepest decrease right here at our inflection point. Then it's going to decrease, but not as much, not as steeply, until we get to our relative minimum. I didn't get the right y value, but I can fix that easy enough. Now we are switching to increasing because our derivative has become positive, and it's going to increase steeper and steeper and steeper until we get to our, whoops, I didn't get that the right place, hold on. So it's going to be increasing, let's see, here was our minimum, steeper and steeper until we get to there is our inflection point, and then by the time we get to zero, that's going to be our relative maximum, so that wasn't the right guess there. And then it's going to now, our derivative is negative, so our function is going to be decreasing steeper and steeper till we get to the place where it's decreasing. I didn't quite get to the right place. It's decreasing the most steeply, and then it will continue to decrease because our derivative is negative till we get to that minimum value right here. And now our derivative is positive, so we're increasing until we get to this x value in here. And then it's going to, whoops, our derivative is positive all the way along here to the end, but it's getting closer and closer to 0. So that means we're going to approach some unknown horizontal asymptote from below. So it's going to look something like that. Okay. Going to slide up a bit here. So now here's some of our more exotic derivatives. We're doing the same kind of thing we did before, only our derivative graph is not going to be so nice and smooth. So, or I'm sorry, here's our function graph. So here's our function graph. We're trying to get its derivative. So a horizontal line has a slope of 0. Now when we get to the corner point's going to be undefined. So I'm going to put an open circle there. Now along a line that's not horizontal, it's going to be just its slope, which it looks like is a -2 in there. So I'm going to go to -2, and I'm going to put open circles on each end because we have corner points on each end of that little line segment. The next line segment here has a slope of +1, so I'm going to jump up to here, and it looks like we have corner points on either endpoint there as well. Now I'm trying to show here, but not really all that great. That's supposed to be a vertical tangent. So maybe I should make it look a little more kind of steep in there. So I want to make that look more like it's going to be right vertical right at that point there. Going to have to use your imagination. So our slope is going to be, it looks like a little bit negative in there. So there's where our corner point's going to pick up. And then it's going to get steeper and steeper and steeper negative and fall off the cliff in the negative direction. It's going to go to -infinity. Now immediately on the other side of that vertical asymptote, it is still going to -infinity. Then it's going to work its way up to 0 where we have a horizontal tangent. Now this next part here is supposed to look like a cusp. And so this is going to go steeper and steeper and steeper towards +infinity. So it's going to do something like that. Now on the other side, this is going to be a -infinity. So our cusp is going to have a vertical asymptote in the derivative, but it's going to be different infinities, whereas the vertical tangent went to the same infinity on either side of our vertical asymptote. Now it looks like we have another corner point in here, but that looks like it's maybe, I don't know, a -1 or something like that. So I'm going to end the derivative graph right here because it's undefined. Now I'm going to switch here. It looks like, I don't know, maybe a +2 or +1 or something like that. Now the next part that we get here, this is supposed to look like a parabola that opens down. So when we differentiate something that's got an x squared in it, we're going to get a linear. It's going to be a straight line, and we know that it's got a horizontal tangent there, so it's going to cross the x-axis right there at our 1, 2, 3, 4, and go to there. Okay, so there is our f' graph. Okay, I'm going to slide it up a little bit. Now we got to change our thinking a little bit here, because now we have a graph of the derivative and we're trying to get the graph of the original function, and we need to make f continuous. So along here is our derivative that is always -1. So that's going to be a line that has slope -1. So I'm going to make it do something like that. And we don't know any y values, so you can start your graph wherever you like. Here we have a vertical asymptote, and it's going to the same infinity, to -infinity. So that means we're going to get a vertical tangent. So I'm going to try to make that look like it's got a vertical tangent there, and then it's going to come out of that vertical tangent here. By the time we get to this value here, our derivative needs to be, our function needs to have a horizontal tangent just for a moment, because then it's going to start increasing because our derivative is positive. So this is going to be where the derivative goes from negative to positive, is a relative minimum. So now it's going to start coming up here. Looks like it's going to positive infinity on one side of that vertical asymptote and a negative infinity on the other. That's going to be a cusp. So and I just happened to end up at a y value of -2. That was just the way it worked out. That wasn't by design. And then we're going to come down, and it looks like that's going to be still decreasing there. And it looks like it's got a slope of about -1. So let me make that still be a little steeper. So it's going to come down in here. Now we see that our derivative is undefined, but our original function is continuous. That means this must be a corner point. So now its derivative is 0, so we're going to move into a horizontal line segment there. That's supposed to be a horizontal line segment. And then we're going to connect that to, again, we have a corner point right here. And now we have the derivative is a straight line. That means that the function whose derivative is linear is going to be a quadratic. So I'm going to get a parabola, and we know we're going to get a horizontal tangent right there. That's where the derivative goes from negative to positive. That's going to be a relative minimum. So it's going to do something like that. Okay, there's our function. And the y values are negotiable, because we don't really know what those are. Now, the next one, here we have only a few values of f, and it doesn't tell us any information. We don't know that f is continuous or differentiable. All we know is a few values. So part A, must f of x be equal to 0 somewhere on that interval? Well, at first glance you might say, well, here it's -1 and there's 3, so certainly somewhere in between there it must be equal to 0, which would be true if we knew that f was continuous. Since we don't, then we don't know for sure that there isn't some kind of discontinuity and the function jumps from a negative to a positive. And so we are going to say no, not unless f is continuous. So if it was continuous, then we could use the intermediate value theorem, but not in this case. Now, to approximate f prime of 3, well, we don't know the value of the function at 3. There's no way we can know what the derivative is, but we can approximate it using a secant line, or our average rate of change. So we're going to take f of 4 minus f of 2 over 4 minus 2. And that's going to be our approximation to the slope of the tangent line, or the instantaneous rate of change. So f of 4 is 7. And f of 2 is 3, and then 4 minus 2 is 2. So that looks like 4 over 2, or 2. So that's our approximation to f prime of 3. Okay, now let's see what we can do with some implicit differentiation. Okay, so we have, we're trying to find y double prime. So first we're going to find y prime. So differentiating, we're going to get 2x plus, here's our chain rule derivative, 2 times y to the first times the derivative of y, which is y prime. You can do this a couple of ways, but people seem to like if we call this minus the first times the derivative of the second plus the second times the derivative of the first, and the derivative of 0, or 1 is 0. So if we distribute that negative sign, then we're going to get a minus x squared y prime and a minus 2xy, and that's equal to 0. We're going to keep the y prime terms here, and we're going to move the non-y prime terms to the other side. So that'll be 2xy minus 2x. We'll factor out the y prime, leaving 2y minus x squared. And we still have this stuff waiting on the other side. Finally, we're going to divide that over, so we'll get 2xy minus 2x all over 2y minus x squared. So there is our y prime. We can evaluate this at 1 and negative 1 to see what that's equal to. We're going to need that in a moment in order to find y double prime. So we're going to get 2 times 1 times negative 1 minus 2 times 1 all over 2 times negative 1 minus 1 squared. So that looks like a negative 2 minus 2 on top and a negative 2 minus 1 on the bottom, negative 4 over negative 3. Uh-oh, I think we're going to have some ugly arithmetic to come. Oh well, we'll plunge on. So now we're going to come up to here and take the derivative of y prime. So y double prime is going to be a quotient rule. So we have the denominator times the derivative of the numerator. So 2xy is going to need a product rule. There's the first times the derivative of the second plus the second times the derivative of the first. And then we get a minus 2 from the negative 2x. So there's denominator times derivative of the numerator minus the numerator 2xy minus 2x times the derivative of the denominator, which is going to be a 2y prime minus 2x all over the denominator squared, which is going to be 2y minus x squared squared. Okay, let's plug in the numbers and hope we get a little bit lucky here with our 4/3. I'm not very optimistic. So we're going to get 2 times y, which we said was negative 1, minus our x was 1 squared, and then 2 times x was 1, and here's our y prime, which is that 4/3. Not looking good. Plus 2 times y, which is negative 1, and then a minus 2, and then minus, we have 2 times 1 times negative 1, minus 2 times 1. Did I get that? And then we have a 2 times, here's our 4/3 again, unfortunately, and then minus 2 times 1 all over the denominator, which is going to be 2 times negative 1 minus 1 squared squared. Okay, let's see. 2 times negative 1 is negative 2. Minus 1 is going to be a negative 3. 2 times 4/3 is going to be 8/3. Yuck. 2 times negative 1 times a negative 2 is going to be a plus 4. Then we have minus, whoops. That's going to be 2 times 1 times negative 1 is a negative 2 minus 2. And then here we go again with an 8/3 minus 2. And I think in the denominator, we're going to get negative 2 minus 1 is negative 3 squared is going to be 9. Okay, let's see. We got 4 is going to be 12/3 plus 8/3 is 20/3. Oh, look at that. The 3's canceled. That's the first good news we've gotten. It's going to be a negative 20. Minus, let's see, we've got a negative 4 right here. 2 is 6/3. 8/3 minus 6/3 is 2/3. No luck here. That's going to be a negative 8/3, I believe. And that's still all over 9. So that's going to be a negative 20 plus 8/3 over 9. Okay, so 20. 20 is going to be a negative 60/3 plus 8/3 is going to be a negative 52/3. To divide by 9 is to multiply by 1/9. And I think actually 52 I don't think we can do anything with that. So I think our sad answer is going to be a negative 52/27. Whew, that was messy. Okay, now this one we're just going to find y prime, but we got more challenging derivatives. So sine of x plus y is a chain rule derivative. So the derivative of the outside function sine gives us cosine, leave the inside function alone, times the derivative of x plus y, which is going to be a 1 plus y prime. On the other side, we have e to the u du. So we have e to that same exponential times the derivative of x times y takes a product rule. So we have the first times the derivative of the second plus the second times the derivative of the first. We get a minus 1 and a 2y prime from the y squared. Now we're going to have to distribute here because we have one term that has a y prime and one that doesn't. And so ultimately they're going to have to go to different sides of the equal sign. So distributing that cosine of x plus y and distributing the e to the xy is going to get us to, I think, this position right here, still with a minus 1 and a plus 2y y prime. So let's see, I'm going to bring the y prime terms to the left. So we have our y prime and the cosine of x plus y. I'm going to move the 2y prime and the xy prime e to the xy to the left side. That's a minus xy prime e to the xy and a minus 2y prime on the left side. So we still have this y, I gotta make sure that doesn't look like a negative sign, a y e to the xy minus 1, and we're going to move this cosine of x plus y to the non-y prime side. We'll factor out that y prime, leaving a cosine of x plus y, a minus x e to the xy minus 2y, and this stuff is just waiting. And then we're going to divide all of that stuff that we factored out to this side, the cosine of x plus y minus x e to the xy minus 2y, getting rid of that, and that is going to be our y prime. Messy indeed. Okay, moving on, here's going to be our 3-link chain rule function inside the cotangent function inside the fourth power function. So its derivative is going to be, first we'll do the x to the fourth part, 4 cotangent to the third of 2x cubed, now times the derivative of cotangent, which is a negative cosecant squared of 2x cubed, and then finally times the derivative of 2x cubed, which is a 6x squared. So we'll bring the 6x squared, the negative, and the 4 all together out in front. So that's going to be a negative 24 x squared. Then we've got our cotangent cubed of 2x cubed, cosecant squared of 2x cubed. And I think we're good. There's our answer. Okay, next one is going to be a quotient rule with chain rules all over the place. And then a bunch of algebra at the end. So we have our denominator, 3x plus 1 to the fourth, times the derivative of the numerator, which is a chain rule. 3 times 2x minus 5 to the second, times the derivative of 2x minus 5, which is a 2, minus the numerator, 2x minus 5 to the third, times the derivative of the denominator, which is a chain rule. 4 times 3x plus 1 to the third, times the derivative of 3x plus 1, all over that denominator squared, which is going to make that be 8. So our calculus is done, but our algebra is only beginning. We can factor out, I believe we've got 3 and a 2, a 4 and a 3. So our least common, or our greatest common factor there is going to be a 6. We've got 3x plus 1 to the fourth and a 3x plus 1 to the third. So we can take out a 3x plus 1 to the third. We have a 2x minus 5 squared and a 2x minus 5 to the third. So we can take out a 2x minus 5 to the second. So what's left, let's see, we took the 3 and the 2 out. We still have another 3x plus 1 that remains. And I think we took out all the 2x minus 5s. Then we have a minus. We took out a 6, but out of that 4 times 3, there's still a 2 left. We took out all of our 3x plus 1s, but we still have another 2x minus 5 here. and our denominator is that 3x plus 1 to the 8th. Well, we can cancel 3 of those, leaving 5 behind. So we're now down to 6 times 2x minus 5 to the 2nd. And if we distribute in the brackets, we're going to get a minus 4x. I think that's going to be a plus 10, still over our 3x plus 1 to the 5th. I'm going to come this way. So we've got 3 times 2x minus 5 to the 2nd. And I think that's going to be 11 minus x is left inside there over our 3x plus 1 to the 5th. That's going to be our derivative. Whew, a lot of algebra. Okay, here we have, I think this is going to be a little optimization problem here. So we want the dimensions of the triangle with largest area inscribed between our curve f of x equals 4x minus x squared and the x-axis with one vertex at the origin. So we're trying to maximize the area of a triangle, which we know is 1/2 base times height. Now we focus our attention on this point x, y. The base of our triangle, because of the symmetry, is going to be 2 times that x coordinate. So there's our base. Now the height of our triangle is going to be the y coordinate of that point. And because that point is on our curve, its y coordinate must be 4 minus x squared. So here is the area function that we are trying to maximize. So if we clean it up a little bit, we can cancel the 1/2 with the 2. We can go on and distribute that x, so that'll be a 4x minus x cubed. So our area is 4x minus x cubed. Let's see if we can restrict our domain a little bit here and make our life easier. Now we could say that x has to be between -2 and 2. We could maybe look a little more critically and see that our base is 2x. So really our x value couldn't be negative. So I think we can actually say that our domain is going to be from 0 to 2. I think we probably have to leave the endpoints open, which is unfortunate, because that's going to mean we can't use our candidate test. But hopefully we'll get, maybe we'll luck out and get only one critical point. So now we're going to take our derivative. That's going to be 4 minus 3x squared. We're going to set that equal to 0. So we're going to get 3x squared equals 4. X squared equals 4/3. So x is going to be plus or minus the square root of 4/3, which is plus or minus the square root of 4 is 2 over the square root of 3. So, I mean, these are not pretty numbers. That's the bad news. But the good news is, on our domain, there's only one critical point. So only x equals 2 over the square root of 3 is on our domain. So we can now look at a very short number line here, because we're only interested in the values of x going from 0 to 2. Somewhere in here is our 2 over the square root of 3. So as we look at that derivative, if we plug in something less than 2 over the square root of 3, say maybe 1, then 4 minus 1 is going to be positive. If we plug in something closer to 2, then this minus 3x squared is going to be bigger than the 4, and this is going to change to being negative. So we can say that our area, A, has a relative maximum at x equals 2 over square root of 3 because A prime changes from positive to negative, period. A of 2 square root of 3, that y value is the maximum because x equals 2 over square root of 3 is the only critical point on the domain. Okay, that's a tough argument, but there it is. That's why it must be the maximum. Okay, let's see if we've answered the questions. I don't think we have yet. We need to find the dimensions. So remember, here's our base, was the 2x. So our base is one dimension. That's going to be 2 times 2 over square root of 3 is going to be 4 over square root of 3. And the height is our other dimension, and that's going to be our 4 minus x squared. So that's going to be 4 minus 2 over square root of 3 squared. That's going to be 4 minus 4 thirds. So let's see. 4 is 12 thirds minus 4 thirds is 8 thirds. So there is our base. So our dimensions, I'm sorry, that's our height. So our dimensions are going to be 4 over square root of 3 and 8 thirds to maximize the area of that triangle inscribed between our parabola and the x-axis. Looks like we have maybe here a little related rates problem. So water is pumped into a cylindrical tank with a radius of 5 feet and a height of 10 feet at a rate of 3 cubic feet per minute. How fast is the water level rising when the water in the tank is 6 feet deep? So here is our volume formula. Now we know that the radius in this tank is 5, and that is not changing with time. But as we pump in this water, and it looks like that's a rate of change of volume, as we pump in that water, then the height of the water inside the tank there is changing with time. So we can say that our volume formula, we can plug in the 5 right off the bat because it is not changing with time. It's always fixed at 5. And so our volume formula becomes 25 pi h. Oops, I left off the pi. 25 pi h. So here the v and the h are both changing with time, so we can differentiate that with respect to t. We'll get dv dt is 25 pi times dh dt. So we can plug in what we know. We know that the volume, the dv dt is 3, and we know that the h is 6, but it turns out it doesn't make any difference. So the rate of change of the height is the same no matter how high that water level is. So our dh dt is going to be 3 over 25 pi, and it looks like that's going to be measured in feet per minute. Okie doke. Sliding down, looks like we have a tangent line problem here. So first, we want to find the tangent line 2f at x equals 10. So to find a tangent line, to find an equation of a line, we need point and we need slope. Well, we know the x-coordinate is 10, and the y-coordinate is going to be f of 10, which will be the cube root of 10 minus 2, which is the cube root of 8, which is 2. So our point is going to be 10 comma 2. The slope is going to come from the derivative. So our derivative is a pretty mild chain rule derivative. So we're going to take 1/3 x minus 2 to the negative 2/3 times the derivative of x minus 2, but that's just 1. So that looks like it's going to be 1 over 3, and then we're going to get the cube root of x minus 2 squared. So our slope is going to be our derivative evaluated at x equals 10. So that's going to be 1 over 3. Cube root of 10 minus 2 is 8. Let's take the cube root first and then square that. So the cube root of 8 is 2, squared is 4, times the 3 is 12, and there is our slope. So part A, our tangent line, is going to be y minus 2 is equal to the slope 1/12 times x minus 10. Now part B, we're going to use that to approximate the cube root of 10. So to evaluate the cube root of 10, I'm going to change colors here. To evaluate the cube root of 10, we need to plug in x equals 12. So we're going to get y minus 2 equals 1/12 times 12 minus 10. So y will be 2 plus 12 minus 10 is 2. 2 times 1/12 is 1/6. So I could leave it just as 2 1/6, or if you want, you could say that's going to be 13/6. Either one of those is equally acceptable. Okay, do I have more? Oh, I guess I do. So the surface area of a sphere is area equals 4 pi r squared. If the measurement of the radius is found to be 6 millimeters with a possible error of 0.02 millimeters, use differentials to estimate first the possible error in computing the area. So we're going to take dA dr, which the derivative of 4 pi r squared with respect to r is going to be 8 pi r. We're going to multiply the differential dr to the other side and get 8 pi r dr. Now we know from the information given that r is 6 and dr is 0.02. So that means our dA is going to be 8 pi times 6 times our 0.02. So let's see, 6 times 8 is 48. 2 times 48 is 96. With 2 decimal places is going to be 0.96 pi. And you're welcome to leave it like that. Or if we put that on our calculator, that's okay too. Let's see, 0.96 pi looks like about 3.0159. So about 3.0159. And it doesn't ask for measurement for units, but that would be an area measurement. And since we're in millimeters, that would be millimeters squared. So our error in computing the radius of 0.02 millimeters means we could be off by as much as a little more than 3 square millimeters in the surface area of that sphere. So the relative error is, we're going to say, so our relative error is going to be the dA over the actual area. So I'm going to go back to the 0.96 pi. There was our dA, and the area means we're going to evaluate the area at r equals 6. So let's see, 6 squared is 36. 4 times 36, I think, is 144 pi. So we can say that that's going to be 0.96 over 144. I'm going to go to my calculator with this. 0.96 divided by 144 is about 0.00, and then it's 6 repeating. So I'm going to say that's about 0.007 to 3 decimal places. So that's going to make the error in computing the percent error as about 0.7%. Okay, very good.